This presentation will cover the analysis of linear array structures for RF energy harvesting done by Group 16. Discuss further in the research paper were the various operating principles and the metrics related to the energy harvesting performance of the array. However, in this presentation, we will elaborate on the test performed and the results to investigate the impacts on the resonator harvesting capabilities in an array by varying three selected array design parameters at a selected frequency band. The arrays were built and simulated using COMSOL on a frequency selective surface FSS structure as perfect electric conductors and used perfectly matched layers on the top and bottom of each resonator. These layers absorb the excited mode from the source port and any higher order modes generated by the periodic structure. The perfectly matched layer consisted of port 1, which was a time-varying magnetic field situated above the FSS, and port 2, which was modeled as a sink located below the FSS. The scattering boundaries were chosen to be all the outer boundaries except the top horizontal layer. This is where the RF energy is to be radiated from. The parameters selected were the number of elements, the amount of distance between each split ring, and the shape of the SRR components. The S parameter plots and EM field norm diagrams were examined.
Here are the S parameter plots obtained for varying the spacing between elements of the array. For these plots, the array utilized consisted of 4 split ring resonators, and the spacing was varied from 20 mm to 30 mm and finally to 40 mm. At a resonant frequency of 4.6 GHz, it was observed that as the spacing was increased, the transmission coefficient decreased, hence more energy was absorbed within the array. The results of the E-field norm plots follow what was observed previously. It was observed that as the elements were brought further apart from each other, the E-field strength between the elements grew stronger. Also, the E-field within the 40 mm space array was stronger than that compared to the 30 mm and 20 mm. For varying the number of elements, only the S parameter plots were studied since the E-field plot showed no variations. For this study, 2, 3, and 4 elements were utilized. What was observed from the plots was that as the number of elements were increased, the transmission coefficient at the resonant frequency decreased, meaning that more energy was stored within the array. This observation was made under the assumption that the amount of energy lost due to scattering was approximately equal for all 3 cases. The results of varying the shape varied much more than previously. For this study, the previously constructed linear array with 4 elements was compared to that of a new array, which was arranged as a square. What was observed that for the square array, the transmission coefficient at the resonant frequency was significantly less compared to that of the array of elements in a line. This indicated that less energy was harvested within the square arrangement than for the line array. Here are the E-field plots of the 2 studied shapes. As you can see, there is a similar field around each element in the line array. Within the square arrangement, there was no similar E-field pattern around the individual elements, as indicated by the varying colors. Comparing the 2 plots within the linear array, there is a greater concentration of red and hence a stronger E-field. Due to applying a time-varying field to the SRR array, as per Faraday's law, an electric potential and hence an electric current is induced in each element, leading to a generated magnetic field. This field induces a current within adjacent elements. As per Lenz's law, this induced current will be in a direction to oppose the change which causes it. For SRRs, this effect is known as mutual coupling. What was observed was that as the spacing between elements was decreased, the effect of mutual coupling became more prevalent. Similarly, in changing the shape from a square to a line, due to a tighter packing within the elements within the square array, there was a greater effect of mutual coupling and hence less energy harvested. If the amount of elements within the array is increased, there is a proportional increase in the amount of energy harvested. In conclusion, a linear array of SRRs for RF energy harvesting was investigated. The 3 parameters studied were size, shape, and spacing of the array. We learned that for smaller spacing between array elements, there would be a reduced amount of energy harvested. And for more elements within an array, there will be an increased amount of energy harvested. These results support the literature review of previous studies. Here are our references, and thank you.